Okay, so the homework problem was to find the flux through each of the remaining 5 faces for this box, which is sitting in a variable electric field. The electric field is given by this vector here. It's 2 times 10 to the 4 times the variable x in the x direction plus 2 times 10 to the 4 times the variable x in the z direction. That makes this the x component of electric field, this is the z component, and the y component is equal to 0. We're going to calculate the electric flux. We have a variable electric field, so we need to use the integral form. The flux is the integral of E dot dA, so it's the integral of EX dAx plus EY times dAy plus EZ times dAz. So we have to use this form because we have a variable electric field. In class, we found the flux through the front face, and we found that result to be 10 newtons per coulomb times meters squared. No direction because electric flux is a scalar. Next, let's do the back face. So for the back face, the first thing we need to do is pick our dA. If we look at our cube here, let's just see if we can draw that back face in there. Make it a 3-dimensional picture. So in here is our back face. Our area element will be a little rectangle. We pick a rectangle because it's convenient, and we know that when we add them all up, we'll get the net area. So dA, from the front face, it's stuck straight out. From the back face, I'll try and draw 3D here. It sticks straight out of the back of the face. So there's our dA vector. For the back face, dA is the area of this, so it has a length of the linear dimension A, 10 centimeters, and it has a width of a little bit in the x direction, dx. So dA is going to be A times dx, length times width, and the direction is out of the back face, so the minus k direction. So that will be minus 0.100 dx k hat. This is a k that makes this the z component of the area vector, dAz, and the x component and the y component will both be 0. So let's put these things together. To find our net electric flux, it's going to be the integral of Ex times dAx, that part's going to be 0, Ey times dAy, 0 times 0 to give 0, and we're left with just the z parts, Ez times dAz. So let's fill that in. We've got the integral of 2 times 10 to the 4 times x times minus 0.100 times dx. Take our constants out front, we get 2 minus comes out front, 2 times 10 to the 4 gives us 2 times 10 to the 3. Integral of x dx. We know that the integral of x dx is x squared over 2. That has to be evaluated at the limits. So we go from one side of the cube over here where x equals 0 to the other side of the cube over here where x equals 0.1 meters or 10 centimeters. So we'll do our evaluation, minus 2 times 10 to the 3 outside of 0.10 squared over 2 plus 0 squared over 2. Do this on the calculator and we get minus 10 newtons per coulomb times meters squared. So that's the flux through the back face. Next we'll do the flux through the right and left faces.